Okay, so this very long word, diagonalization, is a topic that we're going to study at some length. It's going to take us a bit, but let me start with the overall story. So we're starting with a linear map. T from V to V is a linear map. V is a finite dimensional vector space. We're going to assume the dimension is n, and note that we're looking at a linear operator, a map between a vector space and itself. Okay? If we want to find a matrix representation of T, we know that there are many. How do we get these matrix representation? We choose a basis. Once we choose a basis, we know the procedure. We take the basis elements, do T to them, write the results as a linear combination of the basis elements, take the coefficients, transpose, we get T matrix representation with respect to E, right? And there are many of them because there are many bases, right? So let's write that. T has many matrix representations. Given B, a basis, we know, well, somebody might think that this is a matrix, so given a basis B, we know how to construct the representation matrix of T with respect to that basis B. Okay? Take different bases, you get different matrix representations. So our goal is, among all these possible matrix representations, find one that is the nicest. And what does nicest mean is yet to be defined. Okay? But clearly, if we can find one, if we can find a matrix representation that is just a diagonal matrix, that's probably as nice as you can get. Do you agree? All zeros except diagonal elements. Calculating the determinant is trivial. It's the product of the diagonal elements. Calculating the trace is always trivial. It's their sum, right? Raising the matrix to powers, multiplying it by itself is very easy, right, for diagonal matrices. Working with it is extremely easy, okay? So if, here comes a big if. So let's start a new board because I'm going to need some space. Suppose there exists a basis B whose elements are V1, V2, Vn. So this is a basis for V, for the vector space, such that the following property holds. When you take T of V1, V1 is the first basis element, what you get is going to be some vector, so it's going to be a linear combination of the VI's, right? It's going to be alpha 1 V1 plus alpha 2 V2 plus some linear combination of the VI's, right? But suppose it's just some scalar multiple of V1 itself. That's it. That's an assumption. Clearly, that doesn't always have to exist. Or maybe not clearly, maybe it always exists, but in fact, it doesn't always exist. Okay? But suppose it does. Suppose we have a basis such that when we do T to each of the basis elements, what we get is just a scalar multiple of that basis element in that specific basis. So for T of V2 is alpha 2 V2. And I'm writing it here for a reason. T of Vn n equals dot 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 alpha n Vn. Okay? And the reason I wrote it like this is that I'm already thinking I want to construct the representing matrix with respect to that basis. So how do I construct the matrix? As I said, we know we need to write this as a linear combination of these guys. But what is the linear combination here? It's alpha 1 V1 plus 0 V2 plus 0 V3 plus 0 V4 plus dot 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 plus 0 Vn. Do you agree? And what is T of V2? If T of V2 is just alpha 2 V2 for some scalar alpha, then this is 0 V1 plus alpha 2 V2 plus 0 V3 plus 0 V4 plus all the way to Vn, right? And so on. So the representing matrix with respect to the basis B that satisfies this specific property is, so suppose there exists a basis element such that, then T, the representing matrix with respect to this B, is the matrix, the transpose of the coefficients, right? These are all zeros, so it's just this. Transpose doesn't do anything, so it's the matrix alpha 1, alpha 2, alpha 3, dot, 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 alpha n, and all the rest are zeros. Is it clear what I mean by these giant zeros above and below the main diagonal? Okay? Okay, so we're going to call this matrix D for diagonal. It's a diagonal matrix. Good? So if there exists a basis which acts in a very special way with respect to T, to this specific T, namely, T, when acting on a basis element, really doesn't do much to it. Almost fixes it. Almost. Because it does multiply it by some scalar. Then the representing matrix with respect to that basis is going to be diagonal. Clear? Okay. So this is our first goal. Our first goal is to find a procedure which produces such a basis. How do we seek V1 to Vn that satisfy this property? And it'll turn out that it doesn't always exist. Okay? So we're going to understand the procedure of how we find it or determine that it doesn't exist. And later on, we're going to say a bit less, but we're going to say some stuff about what do we do when it doesn't exist. And we can't diagonalize T. This is what it means to diagonalize T. We can't diagonalize T, but sometimes we can do not diagonal, but with a bit off diagonal stuff, but just a bit. Okay? So that's going to be later. So our goals are, so maybe I'll continue writing. So this B is the basis we want to find. The basis B such that T has a diagonal representation with respect to it if such a B, if such a basis exists, we say that T is diagonalizable. I just feel like putting 17 more letters, but that's it. That's the end of the word. Good? Clear? Okay. Now, before we move on, I have to throw in a bit more terminology so we can speak the correct language and understand what we're doing. Okay, so some more terminology. So first of all, we know, and this is going to be a brief summary of stuff that we discussed at length, that there's a tight connection between matrices and linear maps. Okay, the tight connection, which we defined in higher language of the Hom space and so on, being isomorphic to matrices. But in simple words, given a T, we know how to construct a matrix, A. Okay? A is going to be the representing matrix of T with respect to some basis. Let's not call it B, because B is now our specific diagonalizing basis. So let's call it F, right? E is for the standard basis, so let's just call it F. Okay, so choosing an F, starting with a T, choosing an F, we can get a matrix. Starting with a matrix, we know how to construct a map. How do we construct a map? We just define T of V to be A times V, right? So we know how to pass from maps to matrices and from matrices to maps, right? So there's a tight relation between the two, and we made this relation even more precise, right, in terms of what I mentioned before. I don't want to say it again and again in terms of the Hom space, but the point is that we're intentionally going to blur a bit the distinction between maps and matrices. Okay? So for example, we're going to say stuff like the kernel of a matrix. What is the kernel of a matrix? The kernel of a matrix is all the vectors that when you multiply them by the matrix, you get 0. Just like the kernel of T. Okay, so the kernel was defined for a linear map, but we're going to say the kernel of a matrix, and that's what we're going to mean. Okay? I'm going to write some of these definitions a bit more precisely later. For example, we're going to have the determinant of a map. Determinants were defined for matrices. It's a certain calculation you do on the entries, right? What is the determinant of a map? So the determinant of the map is going to be take a matrix representing that map and calculate its determinant. Okay? Clear? And now you may ask, wait, suppose you take the matrix A, which represents it with respect to the basis F, calculate the determinant of A, and say, hey, that's and you got an 8, let's say, and you're going to say, okay, that's the determinant of T. But you're going to take a different basis, maybe E, calculate the representing matrix, and get the determinant and say, wait, that's the determinant of T.
They're similar.
Right. They're similar. You may have gotten a matrix A, you may have gotten a different matrix, C, but they're similar. They have the same determinant. So the determinant of T is well defined. Clear? So we're going to blur the distinction between maps and matrices when it makes perfect sense to do it, okay? And say things like the kernel of a matrix, and say things like the determinant of a map, and so on, okay? We're going to do it formally. We're going to define these things a bit formally later, but because I want to start with just doing an example. Okay, and in the example, I'm already going to use that, but I want you to feel that it makes perfect sense to do so. Okay, good, everybody? Okay, so in particular, we're going to say that a matrix is called diagonalizable. Oh boy, this word is too long. How's that? Diagonalizable. Nah, this is the definition. Let's diagonalizable. So T is called diagonalizable if it has a representing matrix which is diagonal. A is going to be called diagonalizable, not diagonal. If A is diagonal, it's diagonal. But A is going to be called diagonalizable if the T that it represents has another representation which is diagonal. Okay? Which is the same thing as saying that A is similar to a diagonal matrix. Okay? So A is called diagonalizable if A is similar to a diagonal matrix. Good? Good? Okay. So maybe I'll add here. This is so D, the diagonal to a diagonal matrix D, and we know what it means. It means that D equals P inverse A P for some invertible matrix P, which we even know how to find. Okay? So that means that they both represent the same linear map. Okay? So that's what I mean when I'm saying a matrix is diagonalizable. Okay? It doesn't mean that, for example, I can do row operation and get a diagonal matrix. Okay? It doesn't mean that I can... All it means is this. Okay? Good? Okay. So the two questions we want to ask, how do we know if a map or a matrix is diagonalizable? And if it is, how do we find the B that does the job? Okay, so here are the two questions. How do we determine if T is diag, meaning diagonalizable, not diagonal, and if it is, how do we find B, the basis that gives the diagonal form? Okay? So here are some more definitions. Everybody with me? Is the overall story clear? Okay, there's still a lot to do here, but is the overall story clear? The motivation and the theme. Good? Okay. So some more definitions. A vector, V in V, a non-zero vector, now it's hard to read.
Zero would be on top of that D.
Wait, a vector, non-zero vector, here? No, how do we find the basis? Once we have B, we can find D, right? Okay, so how do we find B? That's the, we're gonna find D, the diagonal form, by finding B. That's the, well, in fact, we find both of them simultaneously, in fact. Okay, so if you want, how do we find B and D? The basis and the diagonal form. Okay, okay. A vector V, which is not zero, such that, satisfying, that when you do t to it, you just get some scalar multiple of it, is called an eigenvector of t. This weird word eigen is in German, and it means self or own. Okay, so it's a self-vector of t. It kind of belongs to t. Belongs to t in this sense. Okay. Note, of course, that the zero vector always satisfies this. Right? T of 0 is always alpha 0 for alpha equals whatever you want, for alpha equals 0, or for alpha equals whatever you want, in fact. Right? Do you agree? Right? Because T of 0 is 0 for any linear map. Okay? But 0 is not interesting because we want vectors like this and we want to construct a basis from them. And 0 cannot be a basis element, right? We want a basis. We want linearly independent vectors. Okay, so we're throwing 0 out of the definition. Okay, good? So a vector satisfying this property, which is what we're seeking, is called an eigenvector. And this alpha that does it for this v, and alpha is called, alpha is a number, right? Alpha is a scalar. So alpha is called an eigenvalue of v. Okay, alpha corresponds to this v, which corresponds to t. Okay, so that's not accurate. It's an eigenvalue of, let's be accurate, an eigenvalue of t corresponding to this v, corresponding to v. That's a better way of saying it. Okay, so that's the notion of an eigenvector and an eigenvalue. Okay, and if we go back to a couple boards ago, what we're looking for, now we can say it in a bit more formally, we're looking for a basis of eigenvectors. Okay, we're looking for a basis of eigenvectors. These are precisely vectors that are eigenvectors by definition. Okay, so using this terminology, with this terminology, now we can say what diagonalizable means. T is diagonalizable if and only if it has a basis of eigenvectors. It has a basis of eigenvectors. Do you agree? Okay. And moreover, the diagonal D, right, is a matrix which has the eigenvalues along its main diagonal. Right? Remember what D was. D was precisely, look here a second, D was the diagonal matrix. It had these alphas on its main diagonal. Right? So let's write that. With this terminology, T is diagonalizable if it has a basis of eigenvectors, and the diagonal matrix D has and D is a diagonal matrix with the eigenvalues on its main diagonal. Good? Okay. So this is the framework. Okay? This is the entire story. Now we want to prove some theorems in particular that answer these two questions. And I want to start with an example. Okay? So I want to start with an example that really does the entire, starts with a matrix. The first example I'm going to do is going to be very simple. It's going to be a 2x2 matrix. Okay, very simple. And I want to go through the entire process and figure out what we're doing. Okay, we're going to do it without the theorems and just see what we have to do. And from that, we're going to The theorem is going to stem from the example. Where the theorem is going to say, hey, let's do what we did in the example. Okay? So we'll do that in a separate clip.